In this lesson, we're going to try to use iterative modeling to try to answer the question of what is the big difference between all of these different orbits? What's the difference between Hio? What's the difference between Leo? And what's the difference between Geo? Essentially, are we getting the same bang for the buck for 25 meters per second at Leo as we would at Geo? And then what's going on here with Hio? What is this weird shape that the 25 meters per second burn produced? How is the Hio regime so different from these relatively circular regimes? Well, that's what we're going to explore in this video. For each of these, we're going to have a flyer starting at this same reference point, and then it's going to maneuver somewhere in 1 hour. The way the target sequence is set up, I got my RIC maneuver with radial and in-track burns turned on, and it's solving in 1 hour time of flight to go to some location around the original reference. Along its path, it's going to record the total amount of delta V that it took to get to that reference, and we're basically going to solve for a 200 by 200 kilometer box, and I'll show you that in Analyzer when we begin to run our results. And then we're going to do it for each of the different orbital regimes, and then especially for Hio, we're going to do it at different periods in the orbit because due to the fact that it's highly eccentric, you're not going to get the same results at every single point in the orbit, which is going to be one of the big takeaways from this level of analysis. Cool, so let's fire up Analyzer and let's get rocking and rolling on Geo. Okay, so here we are in Analyzer, and I'm just starting off with a Geo flyer. You go into the target sequence and you get that in-track value and the radial value. Those are your two variables, and then your output is going to be delta V. We'll throw in a design of experiments, in-track, radial. So for in-track, we're going to go from negative 100 to 100 kilometers, and for radial, we're going to do the same to keep things symmetric. Just to keep the level of runs low, we're going to just do every 5 kilometers between these points, and let's just go ahead and get it running.
One eternity later.
Awesome, so here's the Geo data with all the runs complete. From that, it's pretty good to add a contour plot. Which here's a version of the contour plot, and it's the one that we're going to be looking at the most. So I just want to first explain it to you, and then we'll do all the runs for Leo, and then 2 for Hio, and then we'll start to analyze what these time of flight plots actually mean. It's sort of a simple explanation. So if I want to go negative 50 in-track and 50 radial, I should expect to spend somewhere between 15 and 20 meters per second of delta V. So if we jump back over to STK, here's a 100 by 100 kilometer box that I put around my Geo reference, and then here's 1 hour time of flight to that point that we just identified. Negative 50 in-track, 50 radial. And just to get really creative, let's just overlay the graph on top. And so now you can see the overlay of that graph that we just produced with some additional data on it for going to that 50-50 point. So you can see that 50 should have been between 20 and now 17.5 because it's on this tan colored region here. And sure enough, if we go into the maneuver summary of that vehicle, it's going to be 19.447 meters per second. So the chart works. You can put these transparent overlays on any of the charts that you make. I just think it's kind of a cool way to show the heat map against the data that you're looking at. All right, so what we're going to do is we're going to build the rest of the flyers with this exact same 200 by 200 kilometer analysis area. So I'm just going to go in and do the ones for Leo. And important to note, I'm going to do one for Hio at its point of perigee and one for Hio at its point of apogee. I'm also going to do 2 charts for Leo, one that's going to be a 1 hour time of flight and one that's going to be an approximate 6-minute time of flight. And I'll explain why we built all those charts once they're all done. So I'm going to do the exact same thing I did for Geo, and then we'll go into the chart analysis and start to understand the differences between these orbital regimes. Okay, so the charts are done, and let's just start to take a look at the data. As you can see, 1 hour time of flight at Geo is very symmetric around in-track and radial. 25 meters per second gets you about 90 kilometers in any direction, but a 25 meters per second burn in 1 hour time of flight cannot cover a full 100 by 100 kilometer space. In fact, at no point in this time of flight could it get 100 kilometers away from its target in only 1 hour. Switching over to Leo, you can see that the chart looks dramatically different. So it's no longer symmetric around the radial axis, but remains symmetric around the in-track axis. So the reason why these charts look so dramatically different is because 1 hour time of flight is a dramatic portion of a low Earth orbiting satellite's period. If you think of an average low Earth orbiting satellite with a period around 90 to 100 minutes, 1 hour might be 2/3 of that orbital period. And similar to what we saw when we did the analysis for long time of flights for Geo after a single burn, the longer you wait in your orbital period, the further you're going to go in the in-track direction. Essentially, the differences in velocity as you move through more of your orbital period stretch the time of flight range into the in-track axis. So although the area of space that you can cover is dramatically smaller for Leo, you could actually get 100 kilometers away from your starting reference in an hour for something like 17.5 meters per second. My big takeaway for this is if 1 hour is a significant time scale to you and you're trying to fly satellites at Leo, you need to understand that 1 hour is dominated by natural motion. What you're seeing here, this totally symmetric, fighting the laws of physics, I don't care, 1 hour time of flight at GEO, is that force motion at this time scale is highly successful. But force motion at this time scale is going to be scaled according to natural motion. There is a way to get a fully symmetric delta V chart for LEO. You basically have to scale to 1/24th of the orbital period. So this is 1/24th of GEO's orbital period. So 1/24th of a low Earth orbiting satellite's orbital period is going to be around 6 minutes. So here's a 6-minute time of flight, approximate 5.6-minute time of flight because of the orbit that I chose, for a LEO satellite. And as you can see, it's perfectly symmetric and significantly more expensive than the 1 hour time of flight for GEO. So if you want to move in force motion at low Earth orbit, you're going to have to spend significantly more delta V. There's so much nuance here for force motion at LEO that it's probably worthy of a second video. So I'll probably take a look at LEO in a future video where we look at how do you do dynamic station keeping in LEO. If we want to scale that 1/24th of the orbital period to the same colored heat map that we're using for all the other analysis, here's what 25 meters per second buys you in a 5.6-minute time of flight at LEO. Not very far from your original starting location. All right, so what about HEO? Like I said, I modeled HEO in 2 different orbital regimes, and that's because the principles of HEO are dramatically different depending on where you are in the highly eccentric orbit. Specifically, the HEO orbit that we were looking at was a Molniya, so eccentricity is approaching 0.7, a very elliptical orbit. So out at apogee, you're not moving very fast in your velocity. You're essentially hovering over a single location. In fact, you could say that when you're out at your apogee in a Molniya orbit, everything is very similar to the heat map from GEO. So this is HEO, this is GEO, HEO, GEO, HEO, GEO. Other than the labeling changing, it's very difficult to really discern a difference between these 2 charts. So when you're at apogee in a highly eccentric orbit, you fly kind of similar to GEO. However, when you get to perigee and your velocity is moving incredibly fast, faster than low Earth orbit even, you again begin to see the principles of that stretching along the in-track axis. So essentially, if you're a HEO flyer, you have to understand that the time that you're doing your orbit adjustments matter. Again, there's so many strange principles about flying RPO at HEO that, again, it's probably worthy of a second video. So I think we'll deep dive into HEO in a later video. So kind of some big summary takeaways. If you're flying at GEO or you're flying at HEO apogee, force motion is totally acceptable for a 1 hour time of flight. If you're flying in LEO or you're flying at HEO perigee, then natural motion becomes a more significant factor, and you need to understand how natural motion works. If you want to do force motion in these regimes, it's not that it's impossible, it's just going to be significantly more expensive.